naught. So if I define that by this ket notation x alpha, then these behave just like position vectors on in the Hilbert space, or eigenvectors of the position operator. If we were thinking in terms of the conventional approach where we had a set of operators and a Hilbert space of vectors being operated on by the operators, then they behave in just the way we'd expect. So x alpha is an eigenvector of the position operator with eigenvalue alpha delta x. X alpha, the u is just a shift operator within this Hilbert space. So u to the beta shifts x alpha to x alpha minus beta. And the x are also eigenvectors of this, the v elements in the algebra, with eigenvalue omega alpha omega to the alpha beta. We can also define a set of momentum eigenvectors, shall we call them, but bear in mind that these are not now in a separate Hilbert space, these are in the algebra, so we're just talking about single algebraic structure here. So you have the same types of relations that you would expect from an operator algebra with a Hilbert space that it's operating on. But this is...
Are they the same idea? Are they the same minimal ideal, or are they different minimal ideals?
These are in a different minimal ideal. So I should have written it in terms of epsilon alpha betas. You can write it in the same way with the epsilon primes, but then the relation is... I think it's a lot messier in the epsilon alpha betas, which is why I wrote it in terms of...
But it's a lot clearer.
Using of these.
It may be messy.
Okay, it's in a different ideal, which I think we'll see by a relation in a moment. So it satisfies the same things where V is now a shift operator on this space. It just shifts us within this this minimal ideal, and U is just taking us back to the same place. It's just a kind of magnitude operator. So you can certainly see that these are in different ideals. So again, I can define the Bra equivalence. I've got the whole overheads of this from before, but I don't want to put up all the algebraic. Just trust me that you can also define the right ideals in the same kind of way, which are generated by the epsilon alpha naughts rather than the epsilon naught alphas. And we have the relationship between, so the inner product, as it were, between the x's and the p's, takes us back onto this primitive idempotent epsilon naught naught, which we can take as the origin in our phase space, and then the shift operators just move us from epsilon naught naught in space. We know that the Weil algebra is the discrete analog of the Heisenberg algebra. If we look at the commutation relation between these defined elements x and p, then this is the discrete form where s is just this real number given by this sum. And if we take the limit as n goes to infinity of this, then we get this commutation relation I times n delta x delta p over 2 pi. So that so long as in the limit we do the limit such that this thing here stays bounded or stays constant. So we actually have to, if we consider these as our spatial and spatial scale, or the scale in our phase space, in our discrete phase space that we've got here, then these actually have to scale as 1 over root n.
With mathematician's objection, there's an n going to infinity on the left and there's an n on the right, so you want to divide by n.
Yes.
That's
no, because my delta x and delta p go like 1 over root n.
Okay, so then you should have an n also.
It's an odd way of putting it, sorry. I guess it's a non-mathematician's way of writing it. But,
I'm ashamed of you, Nick.
I know, it's terrible what's become of me, isn't it? I used to be a mathematician. I've let myself slip, and I've been in a biology department for 10 years. This is my excuse. That's atrocious, isn't it?
Well, if you just knock the n out, and then... Oh, so you want to...
No, but...
forget it.
In the limit, it goes to I.
Yeah.
So long as
Delta X, delta P.
So long as n delta x delta p
Goes to
of
one.
2 pi goes to 1, it just stays as 1.
Yeah.
So you actually have to define your delta x and delta p
Yeah,
in terms of 1 over root n
Yeah.
in order to get this thing to actually work in the limits in this way. This explicit realisation of it.
Of course, you realise when you wrote the paper you got it right.
I know. Well, that's why I say it's terrible, isn't it? What happens to you? It's, if you don't keep doing these things. So that's what I mean by it anyway. Sorry, I wrote that in a sloppy fashion. So just to summarise, I'm coming to an end now. What we've done here in a very simple toy model, and what Basil was doing this morning was essentially the analogue of this in the continuous case, of looking at how you can take what traditionally is put as a dualistic mathematical structure with an operator algebra and a Hilbert space on which we operate into a single mathematical structure of just the algebra, in which we identify distinguished spaces, the minimal left and right ideals, which are the algebraic analogues of the Hilbert spaces, and Basil showed very nicely that all the structure is in there in the algebra. We're not losing anything, we're not necessarily doing anything different. All you're doing is just representing it in a single mathematical structure, which I think is very important if you're going to go anywhere with the process approach. So this just shows in a very simple analogue of that in this discrete case, how we get out this notion of what really looked like position and momentum in here as part of the algebra as well. So we've already defined a phase space structure on here, which in some ways is trivial, because that's what the algebra is for. It's encoding phase space structure. But it shows explicitly how you can get it out of the algebra in a nice way that doesn't have... So there's my limit that I need. Are you happy with this one? That's what I meant. It shows you without the problems that you get in the continuum limits of having to worry about the infinite dimensionality of it. What I think is interesting about this in terms of the question I posed, or the challenge I posed in the first place, which was, our problem is not to explain what's going wrong at the Planck scale with quantum gravity. Our problem is to explain how you can write down sensible laws of quantum mechanics, well, I say sensible, mathematically sensible laws of quantum mechanics, on a space-time background, and combine that with this idea that everything has to be, all interactions have to be local. Because what writing down quantum mechanics in that way does, in this algebraic way or in the conventional way, it shows immediately that referred to that space-time background, locality doesn't hold in this system. We've lost locality by building quantum mechanics the way we have, by having a separately existing space-time structure. In here, we have well-defined orders on the x and p spaces. Complementarity comes in immediately because they're in different minimal ideals, the x's and the p's. So we can either, if we take the minimal ideals as representing the explicate order in this case, in this toy model, then we can either have one or the other. We can't have the x and the p at the same time because they're in different ideals. And so what we have is that if we look in one ideal, we have a well-defined notion of locality. We've got the shift operator, there's adjacency in here, they're just essentially discrete points on a line, the x's or the p's. The inner automorphisms in here actually represent the evolution of the quantum state, the Schrödinger evolution of the quantum state at least. And if we do inner automorphisms on here, then that preserves relationships within the algebra,